Okay, so let's talk a little bit about homogeneity, polynomial homogeneity, and why we need that, and why this is important property. I mean, we don't really need that, but if we do have that, this is a very nice property. So let's start with the fact that homogeneity, as it's written here, all the terms of the polynomial have the same total degree, and it means that if you see and you look on the terms of the polynomial, for example, if there is variables, we see here x1 to xn, in the equation for the polynomial, in the polynomial itself, each term is to the same degree. Let's call it d in this case. So for example, you see these two variables example, you see that for each term there is x squared times y, and together the degree is 3 for the first one, and for the second term 2xy squared, again x gives 1 power and y gives 2 to the power of 2, so again a sum of 2. So for the two terms we have total degree of 3. So this is a homogeneous polynomial because it's so homogeneous because you can see that each term has the same degree. But for example, for a non-homogeneous polynomial, you can see this one, and you can see that the first term is to the degree of 2, to the second also to the degree of 2 because x gives 1 and y gives 1, but the third is just a free term, which means it's of a degree of 0, so q is not homogeneous. So there is a very important property for homogeneous polynomials because you can take scalars out to the power of the degree of the homogeneous polynomial. For example, you can see this example p, and each variable has a coefficient which is lambda. So for a homogeneous polynomial you can take the lambda out and take it to the power of the degree of the polynomial, and it will be fine. But it works only for homogeneous polynomial. If it was not a homogeneous polynomial, you could not do that, and let's see why. So you can see that it works, and you can see that inside the polynomial the coefficient will always be to the same degree, so we can take it out. But for non-homogeneous polynomial in this case, you can see that the lambda is different in each term, so you cannot just take it out, scale it out as you did for the homogeneous polynomial. Now there are applications for linear algebra, projection, and differential equations, but I'm not getting to it right now. So homogeneity means all terms of the same degree. You can use this property to scale things out, use the scaling property, as you can see right over here, and it's more problem for non-homogeneous polynomials. So we really like homogeneous polynomial. Again, homogeneous polynomial where each term is to the same degree. Non-homogeneous, each term may have different degrees. Anyway, not all of them with the same degree. Some of them can be, but not all of them for non-homogeneous polynomial. Okay, so thank you very much. This was about homogeneous polynomials and the idea of this. If there are any mistakes or corrections, please tell me. Thanks for ChatGPT for writing it down for me, and that's it for now. Thank you very much.